Welcome back. I'm Alan Hall.
I'm Dan Blewett, and this is the UPTIME podcast, where we talk about wind energy, engineering, lightning protection, and ways to keep your wind turbines running. All right, welcome back. This is the UPTIME podcast, episode 25. I'm your co-host, Dan Blewett, and I'm joined here by lightning protection expert Alan Hall. Alan, how are you?
Great, Dan. Just another crazy busy week in wind turbine world. So what do you got on the list of news for the week?
To start off with news, we've got some bird strike mitigation techniques, old ones, old school, aka paint. We're going to talk about a barrage of lightning in Oklahoma, which I'm curious on your take about this, because obviously, you know, a lot of climates are pretty conducive to lightning. Some are not so much. Oklahoma doesn't strike me as one that's crazy, but maybe I'm wrong here. And then our engineering segment, we got some more animal inspiration. So WhalePower, so whale-inspired leading edges, which is really interesting and unique. And then we're also going to talk about vortex generators a bunch, and Internet of Things devices that can help detect faults in the field. So first, let's talk about let's talk about Oklahoma. So 30,000 strikes within 8 miles, or flashes. So I know there's a difference there, but what was your take on this story out of the Washington Post? Why such a barrage of lightning strikes?
I don't, maybe because the Washington Post doesn't see a lot of weather like that, but the Midwest, particularly between, so if you know your geography, like sort of middle of Kansas, south, all the way down into Texas, and even a little bit further north into Nebraska, can be really, really huge thunderstorms. I mean, tens of miles of thunderstorms. And if the weather is right and it's hot and you have enough humidity in the air, and it starts to usually come in from the sort of the Colorado, New Mexico area, it starts to build up and look out. Or in this case, West Texas, you know, it starts building up, and you can get these huge storms. And if they start to churn and it happens at the right time of day, you get these gigantic hailstorms, which and then in turn create all these lightning strikes. And that is not abnormal. I think we're just paying more attention to it now. But if you have the opportunity to drive through the middle of the United States and wonder where all the trees are, that all the trees are small, young, you don't see old trees there, it's because the hailstorm wiped them out. If you get trees of any certain size, they're going to come down. And at one point years ago, this is probably 10 years ago now, Wichita got hit with a huge hailstorm and just wiped out all the trees, just completely devastated the city. So this is not unusual. I think the number of lightning strikes, being able to count them, is unusual. But 30,000 lightning strikes is a lot of lightning strikes. That's
within 8 miles of Oklahoma University is Norman campus. So that's insane. So when you say this hailstorm wiped out all these trees, was it the hail itself, or you're saying like the lightning effects of such a storm?
Just the hail. Just the hail. There's so much hail coming down so hard, so fast, it just started breaking trees, big trees, just breaking them down. And ice storms too. So you've had a combination. Ice storms are bad there too. You're just in the right latitude in the United States where ice accumulates. So Wichita has had some bad ice storms too. They're just taking on all the trees, like to destroy trees. And it's just a combination of the proper temperature, the proper timing, and the way that it's essentially flat there. So once the storms get going, there's nothing to really stop them like there is on the East Coast. So you start building bigger and bigger and bigger, and it just boom. You just get these torrential downpours and these huge storms that are amazing to see. They're scary, actually. It looks like a black wall is headed towards you, and that's what it is. It's a black wall of rain and dirt and lightning is coming your way, and you want to get out of there. And that's where the tornadoes perk up too. So you're right in the middle of tornado territory there. So it's not surprising, because the winds it just gets fed. You know, it just sucks all the air in, spins it up in the air, fills it full of gunk, and drops it on you. Yeah, scary.
That's crazy. Well, speaking of, nature and the effects of the environment and wind turbines. So obviously birds, bats, all these little creatures, they're on everyone's list to protect is, from these wind farms. Obviously there's the noise, but there's also the blades themselves. So this story says basically like even just one black painted turbine blade reduced bird deaths about 70%. So does this surprise you that just something this simple and potentially this obvious would make such a big effect on the wildlife? I mean, that seems crazy.
Yeah, you would think that you would paint them all. Wouldn't you? Wouldn't the obvious answer be like to have you seen? Obviously, you've seen the wind turbine blades, which there's like sections that are painted red and white, and usually that's around airports and where airplanes are flying. But just painting one a different color changes the mix there in terms of bird striking. It doesn't make a lot of sense, does it? Have you ever seen? If you ever look in the inlet of an engine, you got that little. That's what the little cone is on a jet engine today. You see that little spiral they painted on it. That's supposed to be like a little strobe device. When the engine starts spinning, it gets stroby. So I describe it stroby. So it's like strobing. It's supposed to keep birds away. And I don't know how a bird's going to keep away if the airplane's flying at 500 miles an hour and you're just a bird moving at 5 miles an hour. You can't really.
What are you going to do?
The strobe is not going to make any effect, but supposedly it does. And I kind of wonder a similar thing. Is it like a strobe, like because only one of them's painted, that it's like a strobe effect? That's like boom, boom, boom as it spins around, and kind of almost the difference in color indicates there's something. Or does it seem predatory, like a predator or some sort? Because why would the bird care? The whole thing doesn't make any sense. That doesn't. And did you see any explanation of why this works?
Not the one blade. No, I mean it says they had a small. This wasn't a huge group either. Like I wouldn't call a wind turbine a subject, but I mean, the birds wouldn't really be subjects either. But it says in 2013, there were 4 turbines in the test group that had a single blade painted black. And the 3 years that followed, there were only 6 birds found dead. By comparison, 18 bird deaths were recorded by the 4 unpainted control turbines. So I don't know, not a huge, you'd want a much larger sample size, I think, to have really good data here. But yeah, they don't explain why just the single blade was black, because I was thinking that if they're all black, then they have contrast with the sky.
Yeah, it could be.
I don't know what it is exactly. I mean, especially on overcast days, they're going to blend in pretty well. But
there was a while there where the thought was to paint the blades black to get ice off the blades, basically make them warmer when it's cold outside, right? And so you saw that several years ago, and now I've seen very little of that. Pretty much all the blades are white. I assume when you just don't want heat in blades, it's usually a bad mojo there. So they don't paint them all black, and they do other things for the ice today. But is this similar to the bat repellent system, where they're using ultrasound to push the bats away from different areas? That's a cool technology, but that has research behind it, like a lot of research behind it, and a lot of study by people who know bats. This seems like just like an introductory study that maybe need a little more research, because to think about it. I mean, there are tens of thousands of wind turbine blades, hundreds of thousands of wind turbine blades across the world. That for painting every third blade black or whatever color it needs to be, it's a lot of work. It's just a lot of work. So I'm not sure that makes sense in terms of, is there anything else that could repel the birds? Because bird deaths are important. It's just, what's the most effective way of doing it?
Yeah. And you wonder if, I don't know, they could just start to do these things as they roll off the factory floor. Like, hey, you're going to install 100 different turbines. Can we, use 30% of them for a study? Can we just factory paint, those 30 black?
Yeah.
It doesn't seem like that'd be too big a deal. It's not going to affect aerodynamics. It's not going to affect anything except the way they look, which, maybe not that big of a deal. I don't know. We could start hot pink, neon, you never know.
This needs further study. We need to check different paint colors, metallics, right?
But this does bring up an interesting point, which is when you start thinking about the history of things that, for example, humans eat. How did we ever discover that coffee was good to drink? You know what I mean? How do you even know any of these things until you test it? Maybe orange wind turbines are like the way to go. Like animals could just recognize them and avoid them at all costs. Like a lot of these things, like you couldn't test every iteration of it, but lots of times it's just by happenstance where you're like, oh, we accidentally did this thing. I accidentally ate these beans off this tree, and I accidentally roasted them and made them into a brew. Which again, like how we how we have some of the things that we have is baffling. Like people just had to try it once. But
Well, yeah.
but you never know. Like it should be lots of little things. Like we've put a couple little like mirrors glued to it, where it's just like reflecting a little bit of sunlight.
Right.
Maybe like signals birds where they see it, and you never know. There's lots of little ideas that if they went outside the box and really were just tinkering almost, maybe they'd find just by happenstance some strange solution that actually, it's like, why didn't we think of that? That seems obvious now, but you never know.
Yeah.
Because the paint seems like a very fundamental, easy thing to change. Mm-hmm. But yet they've all just been only white for forever, with some exceptions, but not that many exceptions.
There's a reason for that, right? You want to keep the blade. You don't want thermal differences, large thermal gradients to be built up in the blades, and heat added to composite structures isn't good, period.
Yeah.
So, white provides a baseline average temperature and controllable. You understand it, and it helps you be able to see. Let me give you the negative side of painting things black. If you take a lightning strike, it's going to be a lot harder to tell it on a black blade versus a white blade, because a lightning strike leaves soot and dirt and other stuff behind. You won't be able to see it, right? So there's other aspects to the color that are not necessarily intuitive to people who are studying birds, but to the engineers that are sitting behind the desk trying to make these things go. I would guarantee you, having been in those sort of environments, there will be 100 reasons why they will never paint them black. And one reason why they would like to paint them black. So it's that risk reward sort of thing that needs to happen here. Like, okay, we saved some birds, but the reason they're white is so the blades don't fall off. Okay, we need to weigh that out and figure out other means of making it happen. But it is a cool data point, because you need to pick up that data point and say, oh, maybe this is something that we can implement in a different way and get the same result, right? Mm-hmm. Yeah, I think that's the part about it.
All right, so we're going to jump to our engineering segment here and talk first about whale-inspired blades. So this is really, it feels quirky, but it's definitely not. Like, obviously, there's a lot of pages out of Mother Nature's book that have been taken in the aerodynamics world, right? So like the trailing edge serrations are out of the owl's playbook, essentially, like the fringes that help smooth airflow on the trailing edge. And so in doing some of this research, I found WhalePower. So this is a company that they have patented the tubercles that are on the leading edge of a humpback whale's fins. So these like bumpy, and they look super unaerodynamic. I mean, when you think of aerodynamics, you think of like sharp, smooth blades, not like big knots. But Alan, how do these tubercles work on a WhalePower tubercle technology turbine blade? Like, what is the technology there?
Well, it's essentially like the vortex generator. It doesn't work exactly the same, but it's similar in terms of what the result is, which is you want to control, in the case of a whale, where water flows, right? So they essentially have big wings, flippers, and that the whale's using for a little bit of propulsion, but mostly just kind of like a submarine to go up, down, left, right. So if you think of a whale having wings, that's essentially what it is, and you want to be able to control the flow of water over those things so that you can steer all the time, even in high angle of attack situations. So in like a fighter jet aircraft, you want to be able to make that aircraft highly maneuverable. And so you want to control the air over the surface of the wing or the fin and high angles of attack. Right. So in an aircraft situation, you want to be able to turn the aircraft up, like go straight up immediately and get out of the way of enemy fire. In a whale situation, it probably wants to turn very quickly to go get the food, right? The food source, the squid or whatever it's trying to grab. So being agile is very important for a large creature like a whale. And in order to do that, you have to have very essentially active control surfaces. So you need control of the airflow over the surfaces all the time, or the water over the surfaces. And the way you do that is you sort of trip the water, the flow over the entire fin. So instead of the water sort of separating from the fin, you're keeping it rolling over it, which allows you to provide the force you need to make a quick turn for such a large creature. Very similar to the way an aircraft works, or a ship works, or a submarine works. It works very similarly, but the thought process is the same. Always control. If you're controlling where the water or the airflow goes, you always be in control of what's happening. Instead of being an artifact of nature, you can actually control nature a little bit. So evolution here is play a little bit of a selection process where probably the more agile gets fed better because the things you're trying to eat are getting more agile. So it's an interesting technology, right? Very yeah, you like you said, it's like similar to the owl feathers, or to a number of this. If you remember the swimsuits, the Olympic swimsuits from a couple years ago, that had that sort of the roughened surface, which was similar to a shark or a dolphin. I think a shark has sort of like a sandpapery surface to it, which makes it glide smoother, takes less energy to propel through the water. And we've stolen a lot of those things over time as we realize how they work, and then we implement them and make our world a little bit better. So it is. I wonder how they came across this concept. I mean, who's studying whales like that? I guess somebody is.
I think that really was, the guy I just think was interested in studying whales, and you never know where inspiration comes from, but I just think it was something innocuous. I remember reading the story, but I can't find that at the moment. But yeah, I mean, to think that, again, what looks really not aerodynamic is actually very aerodynamically efficient is just really fascinating. That, because again, like you look at humpback whales, they're not like dolphins, right? They're not like sharks. They're not like manta rays, like these really streamlined creatures, like not at all. But yet, when you start thinking of how they move through the water, it's just really interesting. So obviously, do you see this being adopted potentially? And I don't know the viability of this company right now. They're a little bit hard to find. There's a bunch of research articles about them, but beyond that, it's hard to tell how active the company is, I guess is a good way of putting it. But do you see this being like a commercially viable thing?
It's possible. It is possible. So there's a difference between. Because I was having this exact same conversation this last week about one of the products that we're developing. Is the concept is awesome, but the implementation of that concept has to be just as good or better to propel it into some sort of marketplace. Because if you can't communicate the message, if you can't demonstrate that it works, if you don't have any sales, it's just going to fall flat in its face. And the hardest part about any of these technologies, the serrated trailing edges, the vortex generators, all this stuff, is until you demonstrate it, you can get it in service and you can sell some of it, it'll never really take off. So in a sort of a larger business sense, you got to drive the sales to push the concept forward. Otherwise, the marketplace won't ever see it as real, right? So you need those early people to take who are a little more adventurous, to try it and to implement it and to show that it works. You build some momentum there, then you get the sort of the doubting next group, that's maybe the doubters a little bit, that will try it. And then, you kind of work your way through those groups. But sometimes some of the best ideas are left at the ground level, at the entry door, because you can't convince somebody else to try it. And it's hard. We've gone through that process a couple of times here at WeatherGuard of having a new product and finding some early implementers and try to work through that. But in their case, it's they're having it sounds like they're having some management issues and personnel issues, which adds to the level of difficulty of trying to get the product in the marketplace. But once it gets exposed and other people can see it, and they've patented this thing, so you kind of wonder how much value that patent has and whether somebody else will pick it up to see if it's worthwhile. A lot of times, I'll give you from the insider's point of view on the engineering side. So if I'm working at a large wind turbine company or an aerospace company, and we hear that there's some cool concept out there and it's been patented. The difficulty is for the large companies is that you don't want to infringe on the patent because you're going to get sued. But another point is like, well, we could probably invent something similar to that, and it'd be less money than buying the patent. And a lot of times management will go down that pathway because it involves less lawyers. So even if the technology is really good and this company has a really key technology, the chances that somebody buys that technology from them I think are usually relatively low, just because there's other human beings involved on the other side who are working for the larger company that says they have pride too. Like, well, if this guy can invent it, why can't we invent something better? And that's the pathway they go down. So sometimes these early ideas, it's sort of like Edison and the light bulb. And the thing about Edison was he actually made the product. I'm not sure Edison would be famous for inventing the light bulb unless he made the product. So like Bell and the telephone. Like Bell didn't make a telephone, will we know Bell's name? Probably not. Their claim to fame is that they made an industry off of their idea. That's the harder part here. And I do think the wind turbine market is particularly difficult to penetrate because you get such large players over a long period of time. So, we'll have to just keep an eye on it and see how it goes because the technology is cool.
Yeah. So we're going to shift back to more aerodynamic stuff, but I want to quickly talk about one of these fault detectors. So, and there's a bunch of devices like this out here. This is just one of them, but this ping monitor is a battery powered device, mounts directly to a turbine's tower. And so what are these typically monitoring? What are they going to tell technicians?
So this is the cool concept that essentially it's a bolt-on device or magnetic device that kind of sticks onto the tower. And it's got a little solar panel on it, and it has a way of communicating to the rest of the world. And it's just a listening device. So it's got a really sensitive microphone attached to it. So you're picking up vibration off the tower, part of it, and then you're picking up blade noise. And you build up this sort of record of what it sounds like. It's like when the physician listens to your heartbeat. They listen for a couple seconds to try to get a sense of, is it beating normally? And then they'll try to see if there's something that, if you skip a beat or there's a double beat or something abnormal happens. Well, the same thing happens here where they're listening to a good blade system or a good turbine system because they listen to the nacelle and everything inside of it too, generators. And they get a baseline, and if that noise changes substantially, it can send out information about, hey, this sounds like generator bearings. This sounds like a blade is broken. This sounds like you got some loose bolts somewhere. So they can sort of predict what the failure mode is, not that they have an issue, but what the failure mode is and where to go look by the noise that it makes. So from one of the things, if you're having an add-on system to a wind turbine, is you don't want to interfere with how the thing works, right? So you don't want to have to plug into their system, put wires into their system, connect to the system, because you can affect the way that wind turbine operates when you start connecting your stuff to it, or you can create failure modes that weren't envisioned and actually cause more damage to the turbine than help, right? So the concept is right, where they don't have any electrical connections to the turbine itself, and they're just monitoring from the outside. But you're like putting a human being outside and say, hey, look up there and make sure that wind turbine is working right. It's sort of similar to that. It's got a set of ears that they're using to listen to the turbine, which is an interesting way to do it because helicopters use sort of a similar thing. It doesn't work just like that. Helicopters have a system, at least more modern helicopters have a system where they monitor for vibration. So is everything spinning in a helicopter? Those things are rattling, shaking aircraft structures. And so they'll listen for changes in vibration frequency or amplitude that may indicate you have some sort of failure. And then send a signal out to the maintenance group like, hey, I think the rotor blade's loose, or you got a turbine issue, or you got a gear issue, or something of the sort, and send somebody to look at it, which is obviously on the aerospace side has saved lives. That system saves lives, and the same thing can happen here in wind turbines. It can save you a lot of money long term, and it seems like a relatively simple thing to go do. Have you seen that implemented anywhere, Dan? I know I've kept an eye out because this company is based in Australia, right? Where it makes the technology. Have you seen it implemented anywhere? I haven't seen a lot of images. I know probably in Australia, they're probably a pretty good corner of that market. That the wind turbine market in Australia is not huge, but relative to the country, it's pretty good size. So I wonder if it's more of just sort of demonstrating it in country and trying to expand the growth out to other parts of the world still.
Yeah. It says they're operating in the field and that there's 150 on their way to U.S. wind farms. So it sounds like it's something that's starting to expand its reach around the globe. So
did they give an example how much that system, what the cost is for that system? Because it seems like it's a simple kind of stick it to the tower.
Yeah,
setup.
It doesn't seem like it'd be overly expensive, but I'm sure just like anything, there's probably some subscription fees to monitor it, have the cloud software, that kind of stuff. But that's my guess. With all those like lower cost devices today, they're always attached to some sort of recurring revenue stream. So that's kind of what I would assume would be the case here.
Would this thing be? I'm thinking of sort of the Daniela Sky Spec of the drone inspections, because they can do drone inspections of wind turbines so quickly right now. Is this something that would then is a thought that this system would ping sort of a Sky Specs to go out and take a look at the to look at the turbine? One of the things that Danny was talking about is having sort of Sky Specs on site, having drones on site at different wind turbine farms to go look. Like, would it be an automated system where the ping system says, "Hey, we got an issue on this turbine," and the Sky Specs drone goes, "Oh, yep, sure, here we go." Boom, up it flies and scans it and sends the data off to whoever's looking at the data as an automated inspection system. Is that kind of where this is going? Because it feels like that.
Yeah, it seems like that. Yeah, because obviously there's got to be some implication of, okay, we can monitor stuff, we just don't want to monitor it. So,
right.
How can we integrate this with other technologies to say, okay, we've got this rumble, which we're pretty sure is this thing needs attention. So what can we deploy quickly to do that? But
right.
Yeah, it seems like that's the future at some point, where you just have all these things on site where it's like, okay, this monitor says deploy the drone. Boop, I hit a button remotely. The drone deploys, does its auto scan of the thing, and then sets itself back down. I mean, that seems like that's the future, right? Maybe.
I hope so. Wouldn't you say that's the future? I would think that would be obviously the future.
It seems like it. Yeah, I want to be able to push a button and then a drone like goes and does my dishes for me. So it seems like the way for all of this stuff, right? So then humans can get even busier than we are. So we have all these things that make our lives actually not less busy at all. So. Yeah.
Okay, so it's make us more busy. So the drone's going to make us more busy.
Whole side note. But yeah, we won't go down that rabbit hole. So let's shift gears. Vortex generators. So this is one of these power curve upgrade technologies that are really simple, but can make a pretty big difference as far as efficiency. This one company, SmartBlade, and there's a couple others that sell and install these, but they claim a 2.1% average annual energy production increase over 100 test turbines. So what does this technology do? It seems very simple, like little stick-on, epoxy in place kind of, mostly made of thermoplastic vortex generators, but what's the aerodynamic tech here?
It essentially trips the air. That's what it's trying to do. It's, if you think of it as being like a little shark fin, there's actually usually two shark fins, so they're sort of pointing into the airflow or crosswise to the airflow a little bit. And what happens is it's like a fence. Think of it as a fence that's kind of set to the airflow, so the air actually should tumble over the fence. If anybody ever see a snow fence out in the wild, in the Midwest, there's snow fences all the time. The snow fences for similarly where you're actually tripping the air a little bit, so you don't have big buildup of snow. The vortex generator takes the air that's coming across the front of the blade, trips it, makes it tumble and spiral, and keeps it against the blade surface. Otherwise, if you didn't have the vortex generator there, the air would sort of separate off the surface of the blade and create less power. And turbulence is loss. So you want to get the airflow back on the surface, particularly on the inner third of the blade near the hub, because that part of the blade doesn't generate much power. Most of the power is generated in the outer 2/3. So if you can get some additional power out of that inner third of the blade by controlling the airflow and forcing the air onto the surface, that increases your power production. And if it knocks it up by a couple of percentage points, like we were talking about in aging blades, how the power production drops by roughly 0.5 to 1% per year. So if you can get a 1 to 2% increase by basically peeling and sticking on these little plastic shark fin type devices, or vortex generators, VGs, then it's a real simple mod to do. People are going to do it, and I've seen them more and more and more. 3M makes I think 3M's involved in some of these things where they just basically peel off. It's just a peel and stick 3M double sticky tape to the blade, and it works on the inner third of the blade. Peel and stick can work on the inner third of the blade because the blade speeds, if you think about it, the blade speeds at the tip are like 180 to 200 miles an hour. At the hub, they're a fraction of that. So there's not a lot of, you can do a lot of different things down there to make things stick. So you don't need epoxies and complicated things down there. You can basically peel and stick these vortex generators on. But the key to all of it is controlling airflow. And they only do it to the top surface, right? Because the top surface, like when you think of a wing, the top of the wing is curved and the bottom of the wing is flat. Wind turbine blades are very similar to that. So as the airflow comes over the top of that wing surface, it's where it wants to separate. Once it gets about to the middle of the cord, it wants to lift off and just go tumbling off. Well, these vortex generators sort of force it back down and create the power that you otherwise couldn't get. So it's a relatively simple technology. It's used in all sorts of industries. If you watch Formula One race cars have them, aircraft use them a good bit. Anything that's aerodynamic and moving at relatively high speeds will have vortex generators for controlling the airflow. So the thing for wind turbines is that they've been using them more and more and more to get that power production back up. So as they lose production over time, they can put some add-ons. This is the serrated edges. This is the vortex generators. This is the winglets to bring the power back up again, so they can maintain maximum power output for longer of the blade in wind turbine lifetime. So it's cool.
So let's talk about the root of the blade. So why is that so poor aerodynamically? Is it just because it's more round and it's got to be a little more robust just to,
yeah, it's got to
anchor it
carry
in
a
there?
load. Right, it's carrying a load, and the air speeds aren't high enough. So if you think about it, you use the blades have gotten longer. It's the same reason. So as the blades get longer and longer, even though the towers haven't really changed in terms of the height, you have more interface with the air, which means that at lower wind speeds, you can reach production power levels. So over time, over the last 10-ish, 15-ish years. So what's happened is the towers haven't gone any higher. Essentially, the blade diameters have gotten bigger to intercept more air and therefore produce more power. So it's just the way that the physics are. The inner hub of the blade isn't moving across the air nearly as fast. It's more of a drag thing because most of your power is out in the outer 2/3. So as you make the blades longer, you generate more power at lower speeds, all plus, plus, plus. You just don't get that sort of, at low speeds, power generation on the inner third. It just isn't moving that fast. So it's not intercepting as much air. There's a lot of different dynamics. And one thing you had talked about earlier on another earlier podcast was, as we start to think about not an individual turbine producing power, we're starting to think of each as a group of turbines as a system, the same sort of thing, right? They're thinking about not necessarily putting each wind turbine directly into the airflow because it may interfere with the turbine behind it, but it may want to tilt them slightly a couple of degrees left or right. Same sort of thing, right? So I was thinking about this over the weekend. So I was watching a little bit of Formula One, which I can't really racing. I can't really watch anymore because the person who starts at the pole wins all the time. And not to say they're not great drivers. They totally are great drivers. But we got into a point in civilization where we have enough computing power to determine the aerodynamics of pretty much anything. And it's aerodynamics that tends, and somewhat power, but aerodynamics and engine power that tends to win those races regardless. So if you don't have the best aerodynamicists in the world, you lose those races regardless. And so if you're not spending millions and millions of dollars in the wind tunnel to make and that's why the Formula One race cars look so weird, because they've got, this team of aerodynamicists full time. That's all they do is work on the aerodynamics of the car and the spinning wheels and everything else. That same sort of technology being applied to wind turbines. So you've gone from, if you look at wind turbine blade designs 10, 15 years ago, they look rudimentary compared to what they have today. And you see all these other little things being applied to these older blades to bring them back because now we have the computational power to predict where we can make improvements to the blades, and the new, more modern blades have all the little accoutrements coming with them, like the serrated edges, right? They're coming out of the factory because they add that much lifetime and power generation to the wind turbine blades. So we've sort of reached this plateau, and it makes racing awful to watch, because NASCAR is the same way. In the United States, it's the same thing, where aerodynamics is plays system and part it, and they have to control every single part of the car, because if a little bit of aerodynamic improvement makes you the winner of race after race after race. The same thing is happening. That sort of computational power is being applied to other areas. Aircraft, fighter aircraft, military aircraft, definitely so. Aerodynamics there are crazy computationally. And same thing's happening in the wind turbine industry, where we have the computational power. You can be at your desk and do really complicated computational aerodynamics that you couldn't do 15, 20 years ago. And it's changing the way we do everything in terms of wind turbines. Because we mentioned, was it a podcast or two ago, about GE hooking up with a supercomputer, right? You can imagine now that we've gone from basically copying aerodynamic wing designs off of airplanes to now designing our own wings, essentially turbine blades, based on the aerodynamics and the particular location where this blade may be installed. So different parts of the world may have different shape blades because of the aerodynamics and the types of winds and the peaks and the lows, the valleys of the wind, and whether you're in an ocean condition or somewhere else may change the way they want to change the aerodynamics to maximize it for your particular application. Very similar to the way Formula One racers are maxed out for the environment in which they're racing in. So it's a different mindset now than it was a couple of years ago, 2-3 years ago even. Totally different, because the computational power is so available and the software is so good that we can do things we couldn't have envisioned of a couple of years ago. It's an amazing evolution of computational technology. It really, really is.
Well, and when you think about 1%, most people in our everyday lives, you think like, oh, 1% of like my heating bill going down. It's not a big deal. No. But 1% on one of these 12 megawatt turbines is really a lot, especially over a 20-year span. It's huge.
Yeah, and it's the same thing for Formula One race cars. So for Formula One race cars, having a 1 mile an hour difference, right? Because those cars are going 200 miles an hour, so 0.5% is 1 mile an hour. 1 mile an hour difference will win you those races time after time after time, if the race has any length at all. And the same thing is this on a wind turbine, because we're talking about such high levels of performance, that little incremental gain over time makes such huge differences. And this is where the marketplace comes in, where if you can show that your blade's going to generate more power over a longer period of time, you're going to win in the marketplace.
All right, well, we're going to wrap up today's episode of Uptime. If you're new to the show, welcome. If you're a regular here, thank you for your continued support. Please subscribe to the show and leave a review on iTunes, Spotify, or wherever you listen to podcasts. Don't forget to check out the WeatherGuard Lightning Tech YouTube channel for video episodes, full interviews, and short clips from each show. For Alan and all of us at WeatherGuard, stay safe, and we'll see you next week.